Hello friends and enemies, hopefully more friends and enemies. Welcome to another fun-filled video on the topic of circles. So this is the last one on the topic of circles as it happens. I've thrown in some pretty horrible questions at the end just to keep you on your toes and to show you what sorts of questions you might be in for if the examiner has woken up on the wrong side of the bed. So the idea here being I just want to expose you to as many exam grade questions as I can reasonably in the allotted time of the course, so that you're best prepared to face them in the real thing, having been battle hardened by doing some of the harder ones with me. So let's have a look before we get started proper with the warm-up questions. There's 4 to have a go at, as there almost always is. Try these yourselves first, you know the drill by now, and just use this video only to double check you got them right and make corrections if you need to make any corrections at all, that is. So let's have a look together at question 1. For question 1, it asks us to state the coordinates of the turning point of the function f of x equals 3x squared minus 12x plus 21. So to find the turning point, what we could do here is complete the square. And so what we need to do first of all is to make the coefficient of the x squared unitary. So we need to factorise out a 3 from this bit here. We can leave the 21 on its own. So factorise out the 3, that gives us x squared minus 4x. And we can leave the plus 21 on its own for now. So all I've done here is rewrote this bit in brackets, big squared brackets, because now what we need to do, inside these big squared brackets, we need to factorise yet again. This is where we complete the square. So what we need to do here is put the x squared in brackets with just one of the x's, half the coefficient of the x, so half of minus 4 is minus 2. We square all of that, and then minus off the minus 2 all squared. Minus 2 squared is positive 4, so we need to minus off 4. Then of course plus 21 is still there. Now we can expand the big squared brackets. So we're going to have 3 lots of x minus 2 all squared. 3 lots of minus 4 is minus 12 plus 21. So we've gone from this bit to this to this and to this, always leaving the plus 21 outside of it until the very last step, which is now. So now we have 3 lots of x minus 2 all squared, and minus 12 plus 21 overall is positive 9. So we're now in a position to say what the turning point is. The turning point, when it's written in this form, is always this value here, whatever's minus. If this is a plus, you'd make it a minus, and a plus 9 at the end. For example, what I mean by that, if this had x plus 2, the x coordinate of the turning point would be at minus 2. So therefore, the turning point, be lazy and just call it TP, is going to be at 2, 9. Because I have a 2 here and a 9 at the end. Question 2. We have a discriminant type question. So k is a positive constant. This equation has equal roots. Find the value of k. So like I've mentioned, this is to do with a discriminant. So equal roots, equal by the way just means repeated root. One repeated root. So I'm going to just put in brackets what it means by equal. It means repeated root. So what that means is the discriminant, which we can use this triangle symbol for, has to be equal to exactly 0. So the discriminant is b squared minus 4ac, just to make it clear. So our b is the coefficient of the x, which is 12. Our a is the coefficient of the x squared, which is k, and our c is the constant term at the end, which again is k. So we can just fill these values in. So b squared means 12 squared, and minus 4 times a times c means minus 4 times k times k. So I may as well colour code this in just because I feel in a colourful mood, as it were. So this can be neatened up. So 12 squared is 144, minus 4 times 4 times 4, that's minus 4k squared. We can divide 3 by 4, so we get 36 minus k squared equals 0. Now, importantly here, it does say k is a positive constant. So before we start thinking about square rooting and thinking of positive and negative roots, k squared is going to be 36. This implies that k must be the square root of 36, which is 6. Usually we'd consider both positive and negative square roots, but because k is defined as a positive constant, we need to leave k as being 6. Just a point to mention here, if you didn't read this carefully and you put minus 6 as well, you're risking incurring a docked mark in the exam, so always read the question carefully, even if you think it's second nature. It's an easy thing to miss. Question 3. Got this horrible looking equation with surds, and so we need to solve it. We need to give the answer as well in the form a root b, where a and b are integers. What I'd notice here, first off, is we have a denominator on the bottom of one of these sides. What I'd suggest doing, therefore, is getting rid of that denominator by multiplying both sides by it. In other words, we can multiply both sides of this equation by root 2. So this transforms the equation to something more manageable. So 10 multiplied by root 2 gives us 10 root 2. X root 8 becomes x root 8 root 2. Root 8 times root 2 is root 16. If you're thinking that can be simplified, good for you. I'm going to come to that in a moment. Just making a mess of this pen icon again, rather annoying. And the right hand side of this just becomes 6x. Now root 16 is 4, so we can simplify this and say it's 10 root 2 plus x times 4, in other words 4x, equals 6x. Subtract 4x on both sides, we get that 10 root 2 must equal 2x, and finally dividing through by 2, we see that x will have to equal 5 lots of root 2. And that's ours done. Question 4, we've got to solve this equation. 3 to the power 6x minus 3 equals 81. Write your answer as a rational number. So the key with these ones here, if you've got an equation involving exponents, if you've not done logs yet, which we've not, what we could do is think about getting both bases to be the same. So if you notice here, can we make 81 into a power of 3? The answer is yes. We can rewrite 81 as 3 to the power 4, which transforms the equation into something much nicer to solve. So we'll leave the left hand side as it is. 81, rewrite it as 3 to the power 4. So exactly the same thing, but just rewritten. So the left equals the right. The bases are equal, and the left is equal to the right. So if the bases are equal, and each is equal, then the powers have to be equal too. So, in short, this needs to equal that. So therefore, what we have now, that's an absolute mess. So therefore, we have 6x minus 3 equals 4. Add 3 to both sides, we get 6x is 7. Then divide through by 6, gives us that x has to be 7 over 6. And that's the warm-up sorted out. So let's have a look at the main bit of the lesson. So today, because it's the last lesson, I want to give you as much practice and much input of these past paper questions as I can. So here's one straight away. Let's get straight into it. So we've got this circle C with this equation here, x squared plus y squared minus 6x plus 4y equals 12. First of all, we need to find the centre and the radius of C. So for this one, what we need to do is to get this into the standard form for a circle equation. It's not in the standard form at all. What we need to do is complete the square for the x terms and complete the square for the y terms separately. So what we're going to have here, let's just deal with the x's first. So we've got x squared minus 6x. So instead of an x squared, we put an x into the brackets. We halve the coefficient of minus 6. Half of minus 6, that's minus 3. We square that, and then to balance it, we need to subtract off this thing here all squared. Minus 3 times minus 3 is positive 9, so we minus off the 9. Next up, what we need to do is complete the square for the y squared plus 4y part. So for y squared, we just put the y in the brackets. The coefficient of the y we halve, so half of plus 4 is plus 2. We square all that, then we subtract off 2 squared. Positive 2 times positive 2 is positive 4, so we're going to subtract off 4. And all that equals 12. So now we can neaten this up. So we've got x minus 3 squared plus y plus 2 squared. And on this side we've got 12. So if we add this 9 and add the 4, if we add 13 to both sides, this minus 9 and minus 4 disappear. On the right hand side we have 12 plus 13, which is 25. So now we've got all we need. So the centre, we can use these two numbers here. So the centre, we take this minus 3 and swap its sign, so positive 3. We take this positive 2 and swap its sign, so the y-coordinate of the centre is minus 2. And the radius is just simply the square root of this number at the end. So square root of 25 is obviously going to be 5. Part B. We're told that the point P, which is at minus 1 and 1, and the point Q, which is 7 and minus 5, both lie on C. And to show that PQ is the diameter of C. This is actually simpler than what you might think. If we've got 2 points on a circle, P and Q, and both of them definitely lie on the circle, then the midpoint of them not only has to go through the centre, but the midpoint of any diameter is the centre of the circle. So all we need to do here really is work out what the midpoint of PQ is. If the midpoint of PQ happens to be the centre, if the midpoint is this, then we've proved that PQ has to be a diameter. So we're after this to be our target. So how do we find the midpoint between 2 points? Well, you should know by now, we average out of the x-coordinates. So we do minus 1 plus 7 and divide by 2. And we do the same for the y-coordinates. So 1 plus minus 5 divided by 2. Now normally I'd skip to the answer straight away, but because it's saying show that, I'm just going to make this really clear to the examiner that we know exactly what we're doing in every single step. So minus 1 plus 7 is 6, so we have 6 over 2. 1 plus minus 5 is minus 4, and again that's over 2. So now we may as well just divide 3 by 2. 6 over 2 is 3, minus 4 over 2 is minus 2. And lo and behold, that is exactly the same as what we wanted it to be. So if just make a concluding statement, we're pretty much done. So therefore, what we can say, therefore, PQ is a diameter of C as it goes through the centre. It's going through the centre, and the centre is its midpoint. So there can be no doubt that PQ is the diameter of the circle in question. Now for part C. We're told the point R lies on the positive y-axis, and the angle PRQ is 90 degrees. Find the coordinates of R. We need to think about our circle theorems, because it says point R lies on the positive y-axis. It says nothing about if R is on the circle or not. It might just be on the y-axis and not have anything to do with the circle. So what we need to do here, well, what I'd suggest we do at any rate, is to just do a sketch of the circle. So here's the circle sketched out. So the centre is 3 minus 2, so let's sketch this out here. So that's 3 minus 2. It says we've got P on this circle, so P is minus 1 and 1, so maybe P is about here, say. We're mentioning Q. Now Q is 7 minus 5, and so 7 is to the right of 3 and 2, and it's below, so maybe we're talking here somewhere. In fact, P and Q make a diameter, so we can draw in, on our sketch, a straight line going through P and the centre, and at the other end should be Q. It's labeling Q now. It says R lies on the positive y-axis, so R is somewhere up here. Is it here? Is it there? Is it way up here? We don't know yet. But what we are told is that PRQ, wherever R happens to be, is 90 degrees. So we've got 2 points on a circle, and a third point, which may or may not be, makes 90 degrees. We need to remember this theorem here. Angle in a semicircle. From last lesson. Angle in a semicircle is 90 degrees. In other words, because R makes a 90-degree angle with P and Q is a diameter, then R has to be on the circle as well. So all this is now is we've got P, R and Q, like such, and PRQ is 90 degrees. That can only happen if R's on the circle, by this theorem here that the angle in a semicircle is 90 degrees. So now we know that R isn't only just on the y-axis, but that R is also on the circle. That makes our job much easier. So what we can do is substitute in for x equals 0 into the formula for our circle. So, because when x is 0, that's where it's on the y-axis. So sub x equals 0 into the equation equine of the circle. So if we have a look here, if x was 0, we're just going to be left with y squared plus 4y equals 12. We can then rearrange this. So we get y squared plus 4y minus 12 equals 0. This now factorises. So two numbers that multiply to minus 12 and add up to positive 4, they're going to be positive 6. So we have y plus 6 and y minus 2. Now the other thing to notice is that r is on the positive y-axis. So the y value we're after can't be negative. So normally it'd be saying that y is either minus 6 or positive 2, but because y can't be a minus in this case, we can scrub this one off as a possibility. We're looking at this bracket equal to 0, therefore y has to be positive 2. So therefore y is 2. But because it asks for the coordinates of r, we should really say that r is where x is 0 and y is 2. And that finishes off the first worked example. We've now got a second worked example to have a look at here. So we have a line y equals 3x minus 4, which is a tangent to the circle C. So this line here, as you can see, just touches the circle at this point P, which is 2, 2. The point Q is the centre of C, like here, and we need to find an equation of a straight line through P and Q. So in other words, a straight line going through P and Q, we can draw this on straight away really. We want the equation of the line going through P and Q. So what can we know straight off? Well, we should know from last lesson, if not before, that a tangent meets a radius at 90 degrees. So we can just draw in here that that's a 90-degree angle. In other words, the gradient of this blue line will have to be the negative reciprocal of the gradient of this black tangent line. So first of all, let's work out the gradient of this blue line. We know that the gradient of a tangent is 3 because it's in this y equals mx plus c form. So the gradient of PQ is going to be the negative reciprocal, minus 1, over the gradient of the tangent to it. In other words, just minus 1 over 3. In fact, that 3 is a bit messy, so there. So minus 1/3. We also know a point on PQ because we're told what P is. P is 2, 2. So now we can use the form y minus y1 equals m brackets x minus x1. And because this question doesn't tell us what form to leave the equation in, we can leave it in this form, which is probably the easiest one. And so this becomes y minus a known y coordinate, which is 2, equals the gradient of the line in question, which we've worked out as minus 1/3, and brackets x minus the known x coordinate of the point, which is, again, 2. And that will do. Don't need to do anything else. I will say, though, just if you really want to, you could have written it in the form y equals mx plus c. You could have written it as y equals minus 1/3 x plus 8 over 3. Or, if you wanted to, you could have written it in the form ax plus by plus c equals 0. This could be rearranged to x plus 3y minus 8 equals 0. If you wanted to give the examiner a headache and get him to ask his team leader if this is acceptable, you could do it in any one of these forms, but I really think you're going around the houses and making life hard for yourself if you try it in one of these forms. I would suggest to leave it in this form here. Let's have a look at part B. Part B, we need to show that the x-coordinate of Q is 5. We now know an equation of the line. Okay, so keeping it simple, we know an equation of this line that goes through P and Q is any of these here. I'm suggesting we stick with this one. And so if we take this, what we need to do is just sub in when y equals 1, because we're told that it's on the line y equals 1. So if we sub into this equation that y equals 1, we can see what comes out in terms of x. So this becomes 1 minus 2 equals minus a third, brackets, x minus 2. All we've done here is just subbed in that y is equal to 1 into this formula here, which I've highlighted in yellow. So let's just neaten this up. So 1 minus 2, that's minus 1. That equals minus a third, x minus 2. If we multiply both sides by 3, we get minus 3 equals minus 1, brackets, x minus 2. If we now multiply, or divide in fact, by minus 1 on both sides, we get 3 equals 1 lot of x plus 2. Sorry, x minus 2, what am I thinking? This minus 1 disappears and becomes a plus 1, so just left with x minus 2. Add 2 to both sides, therefore we see that x must equal 5, as we wanted to prove. So we now know the coordinates of Q. We know the centre is now 5 and 1, so we can use this for part C. So part C, we need to find an equation for C. The two main components to working out an equation for a circle are the centre of the circle, we know that, and the radius, which we don't yet know. But because we know P and Q, we can use Pythagoras to work out this length here, this blue line, which is the radius. So let's consider that now. So what's the distance between 2 and 5? What's the distance along here? Well, that distance is 3. And from y being 2, moving down to y being 1 at Q, that's a vertical drop of 1. And obviously this blue line, like I said, is the radius. So using Pythagoras, we can see that the radius squared must be 1 squared plus 3 squared, which is 10. And we can leave it like that when we work out the equation of C. So therefore, the equation of C, you should know this, or be getting to know it by now. It's, in fact, I'll take out that equals sign, technically wrong. It's x minus the x coordinate of the centre, so x minus 5, all squared, plus y minus the y coordinate of the centre, which is 1, all squared, equals the radius squared. The radius squared is 10. And that's it for that example. Now for the final worked example, a past paper, again, question, but I've made the final part of this even more challenging, so I've adapted it from a previous paper. The idea being to expose you to as many really challenging questions as possible with my guidance, so when it comes to the test, you have very few nasty surprises. That's the theory anyway. So let's have a look at this one. Figure 3 shows a sketch of a circle C, centre N, with the formula for the circle in the standard form. So luckily, because this equation is in the standard circle form, finding the coordinates of N, the centre, is really straightforward. We just look at what numbers are inside here. So we take the number in the x bracket, and we switch the sign. So opposite of minus 2 is positive 2. We look at what numbers in the y bracket, it's 1. We swap its sign, gives us minus 1. So that's the coordinates of N. Part B is just as easy, really. So because it's in the standard circle form, this value here is the radius squared. So the radius of C is going to be the square root of that number at the end. So the radius is going to be the square root of 169 over 4. Now, fortunately, these numbers are square numbers, each of them. So the square root of 169 is 13, and the square root of 4 is 2. So the radius of a circle is 13 over 2, which if you wanted to, you could put 6.5. It really doesn't make any odds which one you'd prefer to put down. So A and B, not too much trouble yet. Part C is when it starts getting a bit trickier. So we've got a chord, AB, which we're told is parallel to the x-axis. And it lies below the x-axis and is of length 12 units as shown in the diagram. So now what we need to do is find the coordinates of A and the coordinates of B. So this is where in a moment we'll need to remember some circle theorem results. This is what we need to remember. The line bisecting a chord passing through the centre of a circle will always be a perpendicular bisector. So we can use this to our advantage and fairly easily, once we remember this, apply it to find out what A and B are. So let's just label on the diagram using this fact. So if we just make this perpendicular bisector coming down from N, cutting the chord AB, that must be a perpendicular bisector. So from A to B was 12. Because this is a perpendicular bisector, and both these are radii, we've created now two congruent triangles, and the lengths at the bottom of each of these must be 6 each, because it's been bisected by this chord. So we can label this on. As well, we worked out the radius from part B, which was 13 over 2. So we can label this on here now. So we have 13 over 2. Next, what we can do is think about what this vertical distance here would be by just using Pythagoras. So if I just take this triangle here and focus on this one, could focus on the one on the right, doesn't really matter. I'm going to pop this here and apply some fairly simple Pythagoras work. So we've got a triangle, a right-angled triangle no less. One of the sides is 6. The other side I'm going to leave this as a decimal now because it's just easier to write, and I tend to be lazy. And I'm going to call this distance here D, as in the distance below N. So we can work out what D is by applying Pythagoras. So D is going to be the square root of 6.5 squared minus 6 squared. So you need your calculators for this, I reckon. Well, you don't, but it's just common sense really to use it. So square root 6.5 all squared minus 6 squared. Pop that in, and we get 5 over 2. And so this distance here is 2.5 below N, and either side, 6 units to the left or to the right, lies A and B respectively even. So now we know that D is 5.2, we know that A must be the x-coordinate of N, which, if you remember from part A, was 2, but 6 to the left, so 2 minus 6, and the y-coordinate of A is the n-coordinate of A, which was minus 1, but it's this distance below. So it's going to be minus 1 minus another. I'm going to leave this as a decimal, in fact, minus 2.5. And 2.5 comes from this result here, but it was 5 over 2. And so A is going to be 2 minus 6. So the x-coordinate there is minus 4. And the y-coordinate of A is minus 1 minus a further 2.5, which is minus 3.5. Meanwhile, applying for similar logic for B, we take the x-coordinate of N, which was 2, but because B is 6 units to the right of N, we can add 6 onto it. And like we did for point A, the y-coordinate of B, we take the n-coordinate So we take the y coordinate of n, which was -1, and again, like a, it's going to be 2.5 units below. So it's going to be -2.5 again, just like a was. So if we just compute this, 2 plus 6 is 8, -1 minus another 2.5 is -3.5. And it makes sense for A and B have the same y coordinates because we're told in the question that AB is parallel to the x-axis. In other words, A and B isn't going up or down, it's going to be running completely flat, and so the y coordinate should be invariant along the line segment AB. Part D is where they've edited it to make it even more challenging. So for part D, it says hence or otherwise find the coordinates of point P. So what we need to do here is to pull in lots of knowledge and prior knowledge of geometry, not just circle geometry, but just geometry and symmetry in general. So this is quite a challenge, but I'm going to talk you through it. So my suggestion is to first of all remember that we have two radii here, connecting A and B to the centre. So the radii are 13/2, or 6.5. Because the radius always meets a tangent at a right angle, we can just label in that the angle at A and the angle at B are both right angles. Now we need to remember a circle theorem from the long distant past. So going back to GCSE circle theorems, one of those is that the tangents that meet at the same circle are of equal length. In other words, they're of equal length from where they meet, here, to where they touch the circle. So what I'm trying to say is that AP from here to here must be the same length as BP, which is from here to here. And of course AN is the same as BN because AN and BN are both radii. And so I've got here, if I think about this, AP is the same as BP, AN is the same as BN, and so if I split this down the middle into two triangles, I'd create two congruent triangles, because NP would be a shared side, BP is the same as AP, and AN would be the same as BN. So taking this logic further, what I can say here is that ANP and BNP are congruent triangles, if I split them down the middle like I have done, and more than that, if you put two congruent triangles together, and the line of symmetry is where they join, then it makes a kite. And so ANBP is a kite. And more than that, you should know from GCSE from GCSE shape properties, that the diagonals of a kite, if I just quickly draw in the other diagonal here, they always cross over at right angles. So we know that AB is completely horizontal, so the other diagonal, in other words NP, must be completely vertical. So what this tells us and what this means is that P lies directly below N. P is right below N, and that's going to be useful for working out this problem. So, where to take this? Even still, there's still quite a lot to do. So what I'd suggest we might want to do, first of all, is consider working out this top bit of these triangles. So what I mean by that is just remember that from A to N going across was 6 units, because the chord from A to B was 12 units. We could work out this angle theta, and once we know this angle theta, we can then use some basic trig to work out the length from N to P. So let's work out what theta would be. So what I'm going to do here is just focus in on this right-angled triangle here. Now for this triangle, the right angle is going to be here. Like so. So let's just think of this. So I want to work out theta. I know the angle opposite to theta, So I know the side opposite to theta, which is 6. I know the length of the hypotenuse. And so which of SO, Ka, or TOA relates to both the opposite side and the hypotenuse is going to be SO. It's sin or sine. So if we work out theta by doing sine minus 1 of the opposite side, which is 6, divided by the hypotenuse side, which is 13/2, which in this case I'm just going to write as 6.5. So let's work out what that gives us. So again, you'll need a calculator for this one. So shift sin 6 divided by 6.5, press equals, and you should get 67.38 and something else. Now normally I'd say to round off to 3 significant figures, but finding the angle isn't the final answer. Finding this angle is just an intermediate step. So let's give it to more significant figures than we need to make sure we don't fall for the rounding error trap. So let's call this 67.3801, just to be completely safe. So let's call this angle 68.3801. So now we've got this, let's now consider the full triangle ANP. And so if I take this here and move over here for a second, just to give myself more space and more clarity, what we've got over here, not like that, what we've got over here is this triangle. So I've just labelled in what we had from before, with a bit more clarity, less of a mess. So this is triangle ANP blown up to make it clearer. So we found this angle, which I've labelled here. We know this radius is 13/2. I could now use trig to work out NP. So based on this trig triangle now, think about the sides that we know. We don't know the opposite. We want to work out the hypotenuse, h, and we know the adjacent side, which in this case now is the radius 13/2. We know A, we want to know h, so we're interested in A and h. So with SO, Ka, and TOA, which one of those trig relations includes A and h? You should know it's going to be cos Ka. And so we can write down that cos of the angle, so cos of 67.3801 equals the adjacent side, which is 13/2. I'm going to call that 6.5 just to make the writing a bit neater, over the hypotenuse, which is NP. So we can rearrange this and say that NP, therefore, must be 6.5 divided by cos of 67.3801. At this point we can return to our calculator. Now if you've got that number stored, what I'd suggest is to leave that there. So if you press on and clear it off, that's going to be stored as your ANS. So if you press ANS, it's stored. So what I'm going to do, just to eliminate beyond any doubt any rounding error, I'm going to do 6.5 divided by the answer, rather cos of my answer, because the number that was stored was for 67.3801 to more decimal places. So now if I press this, I get 169/10, which happens to be 16.9 exactly. If you use this value which had been rounded, you wouldn't get 16.9, but because this is a final answer of sorts, you could round back to 3 sig figs and it would round to this anyway. So no worries if you used this value here. But that's not the final answer quite, because we want the coordinates of point P. So all we worked out here is that P lies directly below N, and we now know that it lies 16.9 units below N. And so if we were to go down 16.9 units, then P, the x-coordinate would be the same, it'd still be 2, but the y-coordinate would be 16.9 less than this. So minus 1 minus 16.9 is minus 17.9. So just to write it again, therefore P is going to be 2 brackets minus 17.9. And you can now breathe a sigh of relief. We've done one of the hardest questions we've worked through together. So now, chaps, it's over to you. What you need to do next is turn to page 126, exercise 6E, pure mathematics book. So questions 5 to question 11 do all the E-type questions, and those E questions are the types of questions you might see in an exam. What we're going to be doing as well is we're going to be doing the mixed exercise 6. Some of these questions on circles, not to be too blunt about it, some of them are rock hard, so you need to be practicing these circles as much as you can to give yourself exposure and the skills needed to solve them in the exam. So do work especially hard at these circles, and don't be put off if you're finding them hard, because sometimes they are actually really hard. Keep going at your best pace. Do ask me please if you're struggling, don't suffer in silence, and you'll see me soon. Thanks for listening.